Okay, so today, current flow in dendrites. So previously we talked about the Nernst potential and then voltage gated channels and the action potential, but then they're also all over the dendrites, and then postsynaptic potentials that are gated by neurotransmitter. But what we didn't talk about was how the current flows around in the dendrite. How do you sort of describe or understand the process of current flow? And we mentioned it like before when we said if you're further than a millimeter or two away, the current is gonna fall off enough so that you actually need to have a spike. That was the rationale for a spike, but we didn't sort of say why the current falls off. And so to understand this, we have to understand simple linear electrical circuits. And so let's just put up some of our definitions of the symbols. So the first thing is the current, and you can think of that like flow, amount of flow. Amount. So it's just the amount of sort of water, amount of electrons, amount of flow. And then we have the resistance. But normally when we talk about channels, we talk about the conductance, which equals 1 over the resistance. And that conductance is, you can sort of think of that, so let's write it out, conductance. So that's kind of like the diameter of the pipe. So bigger pipe, more water gets through. So this is amount of flow. Okay, so, and then we have the voltage, which is like pressure. But then we have a new one, which is the capacitance. So we have to understand how current flows in dendrites. We have to consider the capacitance, and the capacitance. So the capacitance? What's sort of an approximate physical model of the capacitance? And what I have called it is a spring-loaded storage jar. So capacitance acts like a little sort of spring-loaded storage jar. So what is that? Well, imagine you've got, so capacitance is usually drawn, like this. So, resistance is drawn like this. So capacitance is drawn like a little break in the circuit, and how does it sort of behave physically? It kind of physically behaves a little bit like you had a little storage jar, and it had a spring on it, and then you can pump a certain, depending on how much pressure you have, you can sort of pump a certain amount of water into that storage jar. That's kind of the way that's the way you should think of it, as kind of like a temporary storage for charge. So we'll put Q for charge. So it's basically a little charge storage device, but it's like a water storage device. And then we have a couple simple equations to relate all these. And the first one we mentioned was, Ohm's law, which is just the easy way to remember it is just voltage equals current times resistance, or current divided by conductance, same thing. So that was Ohm's law, and so that just says that current is proportional to voltage. If the resistance doesn't change, then current and voltage, the curves of current and voltage will be the same. So then there's another equation. The amount of charge that you get on a capacitor is equal to the capacitance times the voltage. So that's an important one. So this is the amount of charge on a capacitor. So if you turn the voltage up, then you'll get more charge. If you turn the capacitance up, you'll get more charge. So they're both, and there's a, if we take the derivative of it, the rate of change of the charge is the same equation, equals the capacitance times the rate of change of the voltage. So if you change the voltage more quickly, that just sort of follows from that you change the voltage more quickly, the amount of charge on the capacitor will change more quickly. That sort of that's kind of intuitive sense. So, and then finally, the capacitance is proportional to the area of the capacitor divided by the distance between the plates. So what are the plates? The plates are, these are supposed to represent the plates. But if we draw that out like if we draw out the plate so we can see some area of the plate. So, here's a wire coming out, and then here's the other plate. And then there's a wire coming out of the bottom. So what are the two things here? Well, first is the distance between the plates. So if the distance, since that's in the denominator, then the smaller distance, the bigger the capacitance. And then area of the plate is here. So if you get more area, you have more capacitance. And what is the capacitance? Well, it's the ability of charges to sort of sit on this plate, and then there's a bunch of negative charges on the other plate that are attracting those positive charges. That's how the capacitor works. So if you imagine some positive charges come down this way, they'll pile up on the plate. When they pile up on the plate, they will repel the positive charges on the other side of the plate, and then some negative charges will be attracted to them. And so that's essentially how a capacitor can store some charge temporarily. In order to get the charges there, somebody had to move them there, and so some voltage pressure pushed them down here in order for them to get onto the plate. I mean, that explains how did they sort of, why did they build up on the plate? They built up on the plate because some voltage drove them there. So what's what do these things correspond to in the actual cell? So in the actual cell, you've basically got the lipid bilayer. So the lipid bilayer are these phosphatidylcholine and cholesterol, all these things that are sitting in the membrane. This is the oily part. And so how are we sort of modeling this with electrical parts? So this is the oily part, and then this is water out here and water here. So it turns out that setup is so oily insulator. So this guy's an insulator, meaning that it doesn't allow charges to go through. That's the meaning of an insulator. So, and there's an insulator here between the gap in the two conducting plates of the capacitor. So if we look at this equation down here, so the capacitance is proportional to the area over the distance between the plates. Well, this is pretty much, it's hard to make any thinner plates. These are like the thinnest possible plates. So the water here sort of serves as the plate of the capacitor. It's got charges in it. And so these are pretty much as close to each other as you could possibly get, so it makes a great capacitor. So it's really easy for charges to build up here and get stored, kind of get stuck to the membrane. So this is basically, the lipid bilayer, because it's got two layers, membrane. And so we're going to approximate that with some electrical circuit parts. And so what are those electrical circuit parts? So basically, we'll start, we'll call this water outside, so that's water outside. And this is water inside cell. So what is our simple model of that? A simple model of that is first a wire, and that wire is representing the fact that the water outside is all electrically connected with itself. It's got there's some saline in it, so it conducts electricity. It can allow electrons to move around. We'll just model that. It's much more complicated than that, but we'll just say we're just going to model it with a wire. And what is a wire? What is the definition of a wire? It's something that has zero resistance. So it has, endless amounts of conductance. So it doesn't, of course, have zero resistance. It's got some small resistance, but for all practical purposes, we can assume that electricity can sort of conduct itself around out there. So that's the outside. And then for the inside of the cell, the inside of the membrane, we model this as two things. So we model it as some capacitance, but also some resistance. So what does that mean? So that means that the membrane is just a single thing. It's just some lipids, a double layer of lipids with their sort of oily tails touching each other. So that's the membrane. But we're conceptually dividing it into two different things. One is some capacitance, which is the ability to store charges on either side of it. And the other thing is some resistance, because it's an insulator, but it's not a perfect insulator, so stuff can leak through it. And more stuff, it has, you can think of this having zero resistance. This is, a high resistance, but it's not the same as nothing. Like, what about like the space in here where I haven't drawn anything? That's what you would call infinite resistance. So, a wire has zero resistance. The white of the paper has infinite resistance, and then places where there's less than infinite resistance, you draw a resistor. So that's the resistor. And then this is the inside of the cell, and this is just a one-dimensional model. It doesn't have any sort of diameter to the axon. In real life, of course, an axon is a tube, but we're modeling it just as a line, just to make it simpler. And then we've got some resistance inside. And what is that? That's kind of the goo that's inside the cell. So that goo that's inside the cell has a resistance. And so what are these things? So this is the capacitance of the membrane. This is the resistance of the membrane, and this is the resistance longitudinal. So that's the little piece of the membrane conceptually modeled as an electrical circuit. But then there's another piece right next to it. So here's another piece. It's got another little capacitor, and there's another resistor, and then there's another connection to the next segment of goo inside the conductive goo inside there. So this is our model. And now what we're going to try to do for the rest of the lecture is try to understand how this thing works. It's not very hard. It's got three parts in it, basically. You've got the membrane capacitance, membrane resistance, longitudinal resistance, but it's not straightforward to figure out how that actually works, and in particular how it works dynamically, like when a stimulus is coming in. How does the whole thing work together? And the whole basis of thinking about this came from something called cable theory. And cable theory was developed for the purpose of trying to figure out whether telegraph cables laid across the Atlantic would actually have anything coming out the other end. So, you get a 3,000 mile long cable with an insulator on it to insulate it from the salt water. And so the question is, if we put something in, like a telegraph impulse, like a little impulse in the other end, are we going to get anything to come out the other end? And why is it cable theory? Well, it's basically a cable with a conductor inside and an insulator. But that insulator is going to have some capacitance. And so you have to sort of consider that when you consider how the current is going to flow through it. So that was actually the analogy, important analogy is that the thing that makes, the most important thing that makes the neuron like a cable is that the longitudinal resistance is low and the membrane resistance is high. So that's why it's like a cable. So it's like a cable because the membrane is like the insulator on the cable, and there's a relatively low resistance inside of it. So if you do cable theory, which is differential equations, that's commonly presented when you're trying to understand how these things work. You could examine cases with an infinitely long cable, because if you're trying to solve the differential equations, you can't, if they get too complicated, it's hard to solve them analytically. So you can have sort of an infinitely long cable or a cable that's infinitely long on one end but has a stop on the other end. And none of those things are very much like real neurons. And so typically what people do instead is compartmental models. So compartmental models, of which this is an example. So this is a compartment right here. It's a little compartment. It has, some longitudinal resistance, some membrane capacitance, membrane resistance. That's a little compartment. And then here's another compartment. And so it would be possible with a circuit like this to make branches in it or change the amount of capacitance if the membrane got a little bigger, So I've actually drawn a compartmental model there. That is a compartmental model of the dendrite, as opposed to a continuous model where we would have infinitely small blops of capacitance and membrane resistance. So, but we're not going to do the equations. I think it's more important just to get a feel for, intuitive feel for how this works. So, to do that, the first thing we have to, so when we first look at this circuit, we have to sort of, what's the most basic thing? Well, we got some things that are connected in parallel, and we got some things that are connected in series, and so we need some kind of rules for how to deal with that. And so one rule is current in series. So current in series is the same. So that means, like, if you have two resistors and nothing else in series like this, the amount of current that goes through them has to be the same. That sort of makes sense. You're pushing some water through them, and if such and such amount of water goes through this guy, the same amount is going to have to go through this guy. But the other thing is if we've got things in parallel, so voltage across, so that was series, so series is just connecting things in. So voltage across parallel is the same. So, and that makes sense too, because if you if you apply this, if at this point you apply a certain amount of pressure, then this part is going to be exposed to the same amount of pressure as this part. It might have a different resistance, but it's going to experience the same pressure. Just the same way as that, in this case, if you run some flow through this guy, the same amount of flow has to go through that guy. So there's a couple other things. So what about this case? So resistance in parallel. So resistance in parallel. That's something we'll have to consider when we talk about dendrites. So if we have resistance in parallel, this resistance will be bigger than this resistance. So if you put two resistors in parallel, that actually lowers your resistance. Did that sloppy? So why is that? So if we take one resistor of a certain value, and then we just put two of them in parallel, we get less resistance, even though you got two parts. And that makes sense from the pipe point of view. So all you did is you made two pipes. So you got one pipe here or two pipes here, you're going to be able to get more water through two pipes. So when you put resistors in parallel, it actually lowers the resistance. But capacitors in parallel is the opposite. So if you put capacitors in parallel, it raises the capacitance. Let's do it again. So just if we take one capacitor, that's going to have less capacitance than two capacitors that are in parallel. And that makes sense intuitively also, just because now you got twice the, if they're the same size, you got twice the amount of plates. So you just increase the area. So it's just like you could sort of glom it into one bigger capacitor. Okay, so those are our basic rules to keep in mind. And now we'll try to sort of apply those to our situation. But let's start off, before we deal with the whole circuit, let's start off with, assume you have a constant current battery to make our life a little simpler. So if we connect this battery up, it delivers a certain amount of current. And so if we have something like that, and we have a switch that we can close, and then we've hooked it up to nothing more than one resistor and then one capacitor, like that. And then it goes back to the battery. So the question is, what happens when we close this switch? So before we close the switch, there's no current flowing anywhere. The voltage is zero everywhere. We've assumed that we've discharged the capacitor. So we're starting at zero. And then if we plot the amount of current that comes out of the battery, so this is the amount of current that comes out of the battery. So the battery, you shut the switch, and then a constant amount of current comes out of the battery. So now we can ask, how does when that current comes out of the battery, so you imagine some current coming out of the battery, and so it comes to this point, and now it's got two possible ways to go. It can go sort of like this way, or it can go this way. So the important thing about a capacitor, before it's been charged, so if capacitor is completely uncharged, it acts, you can sort of think of a capacitor as uncharged, is having the spring is exerting virtually no force on the storage jar. And so it acts like a wire. So an uncharged capacitor has no effective resistance. Of course, it's got an insulator in it between it, so it's got infinite resistance. But if the charges come down here and it's uncharged, they can stick to the plate. And so at the first instant, when you close that switch, what's going to happen is that all the current is going to go to the capacitor, because this guy has some resistance, this guy has zero effective resistance. So that's why I said it's like a storage jar, and when there's nothing in the storage jar, the spring is not pushing on it at all. And so it just acts like a wire. So what will happen is you'll actually start piling up some of the charges on this capacitor. And so if you look at either the voltage across the capacitor or the current going through the capacitor, what you'll see, we'll just draw current here for now. What you see is that all that amount of current is going to go through the capacitor. And then if you look, so this is the current going through the capacitor, and this is the current going through the resistor. So at the very beginning, there's going to be no current going through the resistor at all. But what happens is, as the capacitor starts to get charged, it develops some effective resistance. Sometimes that's called impedance, because it's the actual resistance of the capacitor is infinite, because in the end, once it's charged up, you can't drive any current through it. But at the beginning, it's got an effective resistance of 0, because it looks just like a wire. But as soon as you start charging it up, its effective resistance goes up and up until it gets up to this level. At a particular voltage for a particular capacitance, this much charge is stored in it. At that point, the resistance is infinite. And so what will happen is, the current will start charging this up, and as soon as it gets charged up a little bit, less and less current comes to it, and more current goes to the resistor. And so what that looks like in the curves is that you get less and less current going through the capacitor until it's fully charged, in which case there's no current going through the capacitor. It's not really going through it, but it's sort of piling up on one plate and leaving from the opposite side. So pluses pile up there, but then that allows pluses to go this way temporarily as you're piling them up. Okay, so then what will happen over time, the effective resistance of the capacitor gets more and more, and then what will happen is the more and more current will go through until, so this amount here is the same as this amount, is the same as this amount. So that's a very simple circuit with a capacitor and a resistor in parallel, because we have to understand how that works. Now we'll just take a tiny breath and just draw out a larger chunk of the membrane. So let's draw it in green. Okay, so here's the outside. And so here's a little chunk of the membrane. It's got a capacitor. I drew it the other way last year. I'll draw it that way. So a resistor and a capacitor. And then there's some internal goo. And then another resistor and another capacitor. Another, got to draw like a number of these. Okay, and now we're going to sort of make a cut here, and so this is very far away. So here's another one that's far away. Okay, so this guy is far away. Okay, so now what we want to do is try to figure out what happens if we inject some current like a synapse would. So like a synapse, what is a synapse? So what's our electrical model of the synapse? Well, electrical model of the synapse is, let's go here, and we'll call that sort of this is our electrode. And if we inject open a channel, and that causes, the Nernst potential for sodium or whatever to inject some current into the circuit. So what's going to happen in this circuit? So now it's kind of gotten worse, because the current can go this way, or it can go that way, or it can go down this wire, split up and go through the capacitor, go through this resistor. It could go through this resistor and also through this resistor. So yes, it's more complicated. But let's just start off at the very first instant. So at the very first instant, so what's gonna happen at the very first instant? Well, there's some resistance here and resistance here. It's low, but there's resistance. And there's some resistance here, and all the capacitors are uncharged. So this capacitor acts like zero resistance, because it's like right at the very beginning. It's completely uncharged. So at the very first tiniest instant of time, the current will go through this capacitor. But as soon as that charges up a little bit, what will happen is it will get some effective resistance, and so then less current will flow through that capacitor, and the current will start flowing through these resistors here. So more current is going to flow this way through these resistors because they're low, they're low resistance, and less current, much less current will flow through the membrane. Some will, but less. So now we've got to sort of take all those things into consideration. But if you think about it, it's reasonably straightforward. So we apply some current here, we start charging this guy, and then he starts to get charged. Then you eventually, basically after the smallest amount of time, the whole circuit starts experiencing some pressure. But this guy will get charged also. But let's consider the amount of charge that you end up with after a long time, after everything is settled down, which it does. We didn't describe why it does, but it does settle down. So after everything is settled down and the voltage is not changing anymore, then there'll be a fixed voltage, and there's a fixed amount of membrane capacitance, so we can figure out how much charge there should be. And so what will happen is this guy will be pretty charged because it's near where the current is flowing. But this one down here won't be as charged. And why won't it be as charged? Well, because the current has to flow through these resistors. And so when the current flows through a resistor, the pressure gets less and less. And so the voltage across this capacitor is going to be smaller than the voltage across this capacitor. This guy won't get charged as much. But after a long enough time, it'll eventually get charged up to what this equation says. So whatever the voltage was at that faraway part, times the capacitance, which is the same, and so it's basically, so the amount of charge will just be proportional to the voltage, and the voltage will be less because of having to go through these longitudinal resistors. So that's pretty much, so now you have it. So you stick something in there, you slowly charge up all the capacitors until they reach a steady state, and everybody's charged. Now, once they reach a steady state, once you're in this state where basically you have a constant capacitance, constant voltage, and you've waited a long enough time to charge everybody up, the capacitors act like they have infinite resistance. And so at that point, if you just plucked the capacitors out of the circuit, nothing would happen, because all the current is flowing through the resistors. You'd steal some of the charges, but you wouldn't change the arrangement of current flow. So what happens is you inject current. It takes a little while for everything to sort of like come up to a steady state, but when it comes up to a steady state, no current is going through the capacitors or building up on their plates, and all the current is going through the resistors. Okay, so that's good. But what happens if we turn off the current? So what if we just suddenly switch the current off? Then what's going to happen is the spring-loaded part. So there's like a spring in each capacitor, effectively. And so what will happen is that as soon as you turn the current off, all that current, all the charges that were stored on the capacitor plates, now that the voltage is reduced, will start leaking out of the capacitor and flowing around the circuit. and they'll sort of like flow around the circuit until finally, you know, everything is stable again, which is like 0. So that's what these capacitors do. It's like it sort of gums up the works. You try to change something and some of the stuff leaks into the capacitors. And then you turn off the thing and then some of the stuff swishes out of the capacitors. So what does that look like if we draw some simple graphs? So again, we're starting, you know, like physicists doing these ridiculously simple situations. Like the first situation is, well, let's imagine we just turned some current on and left it on for an infinite amount of time. So the first situation is, you know, what happens if we just turn the current on? So this is time, and this is the current. So if we just turn the current on, and then we can look at it across space, or we can look at it across time. So if you look at it across space, what's going to happen? Look at this. What we're looking at is, so just looking at this, a whole bunch of these compartments, zillions of them. So if you look at it across space, what you'll get is we start off at 0, and then what happens is, so we're at 0, and then we turn on the current, and then what will happen is the current, you know, if we look at the current across space, or we eventually get up to this point here. So this is time equals infinity. This is time equals 0. So after a long time, all the capacitors are charged, all the current's going through the resistors, and then we're in the steady state. So what does that look like if you draw it across time? So if you draw it across time, you'd get something, if you were, you know, near, you would get something that went up quicker. If you were, you know, so this would be, this guy would be, you know, if we look close, it would be there. If we looked further away, it would be here. Okay, so that's a picture. So that's just what we said in words before. You just inject some current here, and it just causes the amount of current flowing through the circuit and the voltage across the resistors to increase until it reaches a steady state. So that, if we had solved the cable theory equations, that's where you would get those solutions from. So what about if we just did, we're still not up to an interesting thing yet, but what if we just turn the current off? So this is 0. So what if we just turn the current, so the current was on and we turned it off? So in that case, it describes what I said second, that there's going to be some kind of sloshing out of the capacitors going on. And so what happens there, so I didn't write this in, this is injection point. So if we do the same thing for turning it off, so that means we'll start at this, so this is time t equals 0, so that's the same as t equals infinity. So that's our starting point. Everything is stabilized for a long time here. And then if you let it go, well, if you do a whole bunch of differential equations, what do you get? Well, you get an excitingly different round thing there. So it's actually round instead of pointy. So what happens is, you know, eventually you get back to 0. And so this is, so at, you know, time equals infinity after a long time. What's infinity? It's about like, you know, a half a second or a tenth of a second. And then you get back to 0. And so what does that look like, you know, across time? It just looks like kind of a fall off. So if I'm close, you know, it's going to be something like that. If I'm a little further away, it looks something like that. So this would be, you know, this guy. So this guy is close. and this guy is, further away. So this is the same data as this, but just described over time instead of over space. So this is x over space. Okay, but we're still kind of like hopelessly abstract, like that never happens to a cell. It's like a voltage clamp. That never happens to a cell. That never happens to a cell. And so what's our approximation of what happens to the cell? Well, normally something like that happens to the cell, but that's even more complicated and makes more complicated math. So let's consider something very simple, which is, let's just assume we just turn the current on for a little bit and immediately turn it off. Okay, so that's time, and this is current. So now what happens? So this is now something that's sort of like an actual synapse. And so what does the graph look like in that case? So in that case, we've got something a little more complicated. So it's a combination of these two things. It's kind of like this for a tiny bit and then followed by this. So what this looks like is, at the very beginning, very early in time, you'll have like a little spiky amount of current because the current only got a chance to start charging up the local capacitor. It hasn't had a very, very long time to be able to spread out. So at the beginning, that's what it looks like. And then after a little while, the current will sort of have spread out a little bit like that. Now, where did that current come from at a later point in time? It came from the capacitors, because you sort of like stuck some current into the capacitors, and now the current is kind of like leaking out of the capacitors. And then after a longer time, you get something like this. And you can see this guy is above. So this is, let's just label a couple times. So this is, t equals 1. This is, time equals 2. This is time equals 3. And then finally, after a long time, we'll just get all the way back down to the bottom. And so that would be, it would be all 0 again. Time equals infinity. Okay, so that's kind of counterintuitive, but how would it look if we just plotted it at a point across time? Now we're finally getting to something that sort of seems slightly vaguely relevant to neurons. Okay, so here's what it would look like. So what would happen is if you were very close to where you were injecting, you would get something that sort of went up and then went down quickly like that. If you were near, what would happen is you would go up and then come down. Now it sort of looks like one of those curves that we always draw. But if you were further away, you'd come up, but it would be a little longer to peak, and then you would go down. You always have to stay under. That guy. Let's just leave out that guy and just put near and far, because that one's right at the injection spot. Okay, so what's going on here? So this guy, here's the peak of that guy, and here's the peak of that guy. So this guy is near. This is time again, remember? So this guy is space away from the injection, and this is time. So this guy is near. So that would be like, say, somewhere here. And then this guy is far. So that would be like somewhere over here. Okay, so what's the point? So the point is that if you do something like a synapse, like do a little injection of current into the synapse, what is that going to have the effect of doing? It's going to have the effect of causing a little disturbance to propagate in time. And if we're further away from where the injection was, that disturbance is going to be slower to peak. And so you can sort of think of it, this is like, so the difference between these two is kind of like the conduction delay. So that's why it takes a while, if you do a disturbance in one part of the circuit, for it to appear in some other part of the circuit. So if I do a little synapse here, it's going to take a couple milliseconds before that effect is visible at a distance. Now, what's causing that? That's the important point. Why do we go through all this nightmare? So what's causing that? What's causing it is the capacitance, the fact that it takes time and work to charge the capacitors and discharge the capacitors. So if you think about it, the neuron is an electrical circuit, and electricity is conducted very rapidly. In a wire, it's conducted like almost the speed of light, like a third or half the speed of light in a wire. But voltage changes in a wire are conducted very rapidly. And so it doesn't conduct quite as rapidly in a solution of goo, but still very rapid. And so why should it take like milliseconds? That's a really long time for electricity. Why should it take milliseconds for anything to happen? It's because of the capacitors. So as soon as you change the voltage here, that's how you inject current, you change the voltage, you're instantly going to touch all the circuit, even the ones that are really far away. You just touch them very lightly. And then over time, eventually they'll sort of like come up, but the ones closer will come up faster. Same thing is happening in the neuron. When a synapse opens up, it effectively touches the whole dendrite all at once, but because the capacitance hasn't been charged, then it's going to take some time to charge those. And so that's really what causes this conduction delay in a neuron. Okay, so in the last negative four minutes, we're going to talk about something that's slightly more practical. So why do we have something like myelin? So it turns out the reason we have myelin is because we want to reduce the capacitance. So if you read about myelin, you immediately must have thought, well, it must insulate the membrane. And you'll find that in textbooks. But in fact, that's not the main effect. The main effect of myelin is to actually increase the capacitance. So what does a neuron look like? Well, here's a node of Ranvier, and here's another node of Ranvier. So the axon actually gets thinner at the node of Ranvier. And then we have the myelin. And so the myelin, what is the myelin? It's just a bunch of oily membranes that are rolled around the axon. There's actually a glial cell comes and it just basically, it probably twists the axon and sort of like deposits layer after layer, like 15 layers of myelin. So you might think that's insulating. Nah, it's not insulating. The membrane resistance is already plenty high. So you can't increase the membrane resistance that much. What it's doing is it's spreading the plates apart. So if here's the capacitor, since that thing just sort of serves, it is sort of insulating, but that's not the main point. The main point is it just spread the plates apart, thereby reducing the capacitance. So this means reduce capacitance. That's the main effect of myelin. And so when you reduce capacitance, what you do is you make them easier to charge up, and so that means more current will be available to go a longer distance. That's the critical thing. So myelin is only found in vertebrates. So what did the invertebrates do? Well, you might have heard that the squid axon is really big. And why is it really big? Because it's trying to increase conduction velocity. And what is it for? It's actually for an escape reflex. And so squids have just a couple really big axons. And what is that really for? It's the jaws of the shark are coming down like this, and they're just about to clamp down, and you go whoo, right at the very last second. You just have a very rapid movement that gets out of the way. That explains why you just have a couple of them, because obviously it would be nice to have everything go fast, but if they're really big, you can't put that many in. And so why does that, so this is a method of, turns out this is a method of increasing, so this is node of Ranvier. This is a method of increasing conduction velocity. And because you've got less capacitance, and so that means this whole effect here will be moved over if we reduce the capacitance. So the impulse, this effective impulse, will be visible more quickly at a distance. So that's the way of increasing conduction velocity. But why do you make a bigger axon to increase conduction velocity? And so I always draw this with little, so here's a small axon. And there's two things that we have to consider, which is the membrane capacitance, three things: the internal capacitance, longitudinal resistance, the longitudinal resistance, the membrane resistance, and the membrane capacitance. And each of them depend on area. And so these are little units of, these little tubes, these are sort of units of area. And here's a little stretch around the membrane, and here's some units of area going around the membrane. And so that area is going to sort of tell you about the membrane resistance and the membrane capacitance. And then these things are going to tell you about the longitudinal resistance. So that's a small axon. So now let's make a bigger axon. Large. So if you make a bigger axon, what happens? Well, here's a much bigger axon. So what happens now is, if we look at the membrane, we're going to see a couple things happen. There's a lot more area of the membrane. So what's that going to do? That's going to increase. It's going to increase the membrane capacitance. That's a bad thing. So that's going to slow us down. And what else is it going to do? It's going to decrease the membrane resistance. Also a bad thing. More stuff is going to leak out through the membrane. We want a good insulator to be like a submarine cable. So both of these are bad. Bad, for conduction velocity. So why do we make it bigger? Well, it turns out, if you look at the cross section here, the amount that the additional number of pipes that we've added is huge. 60 seconds. Okay. And so what this is going to do is make the longitudinal resistance go way down. And that wins. And so the conduction velocity goes a lot faster. Okay, I'm within 5 seconds of the end of the video, so I'll end it there and ask for some questions.